Welcome to Packet Pushers, where discussions around the finer points of technology using power sums, spectral width, and channel composition as well. Not entirely unusual, but it doesn't actually happen every day. Now, I consider optical networking to be a specialized area of networking, and in particular data networking. But for many people, this is really low visibility to otherwise experienced network engineers. I've talked to plenty of people with 20, 25, 30 years experience, and they wouldn't even know what optical networking is if it came out of the bottom of the boat and started biting off their legs. Really, optical network is much less about packets and paths and much more about the physical properties of fiber optic cables, signal propagation, and remote operations. It's about transponders and wavelength switching, things that most network engineers just don't get as part of their standard training. Now, in recent times, optical companies have been moving into data center interconnect and selling products direct to enterprises where you bang what fundamentally looks like a 1RU switch on the back of a dark fiber offering from a provider, and you can now start to provide DCI services, or maybe your least worst telco supplier, which is probably the only one you've got. They're often using this exact same technology to provide layer 2 transparent bandwidth between data centers. Now, sure, L2 transparency is risky, but it remains the only way for enterprise applications to actually work today. The reality bites pretty hard here. We all know L2 is a disaster, but it's still a working solution. So what I've done is I've reached out to a couple of willing victims from the internet. Joining us is Scott Wilkinson from ECI Telecom. He's a senior director in portfolio marketing there, and Andrew Schmidt, who is an analyst at Signal AI. And they're going to be here to talk a little bit about optical network. You can find out more about them in the show notes on the Packet Pushers website, in the blog post of their companies this show. And they're also going to talk a little bit about where they are and what they come from at the end of the show. So let's get right into it. My first question is, I've seen a lot of talk recently about something called silicon photonics and optical components. Now, optical switches tend to be made up of these interfaces, the RODMs that tend to go into the edge. Andrew, is that market really booming? Because my understanding is that's really the key to optical networking, is those transponder modules.
Yeah, the transponder model, that's where the magic happens, right? That's where you take the electrons and you convert it into photons, and that's how you drive it through the fiber. Now, silicon photonics is another way to build the same transponder. If you look at the way things have been done in the past, they use technologies like indium phosphide or lithium niobate, or combine those together to turn the electrons into optics, and specifically you need a material that can create photons, and silicon actually can't. Silicon photonics, what they do is they take a material that can create photons, that can laze, and then they put that on top of a silicon substrate. But the holy grail for silicon photonics is you can take optics and then embed it right into your chip. So imagine a Broadcom Ethernet switch, but instead of having electrical I/O, it would have optical I/O. That's the long-term promise of silicon photonics, but we're a long way from that.
So silicon photonics would be useful then in getting from the ASIC. So if I've got a 100 gig interface on this, today I have a 50 gig electrical interface running a PAM probably. Instead of having a 50 gig electronic interface, I might start going to a 200 gig optical, which then goes off to the physical interface.
Well, that would be the physical interface. You just go right off the chip, right out of the front panel, and off you go.
It would still have to be amplified. They wouldn't be able to laze at the sort of power level that you need to transmit a 100 gig, 200 gig signal straight directly off the chip, would they?
Well, it depends. It depends a lot on how far you want to go and how strong your source laser is and how much it's being split. But in general, yeah, and that's one of the downsides of silicon photonics in longer reach applications. Is it is a more lossy medium. So when you look at people doing 1,000 kilometers, things like that, there are some companies that do silicon photonics, but a lot of the more traditional technologies are still quite competitive. Now, going back to the Broadcom chip example. One of the things, if you actually look at one of those chips today, at least a third, maybe as much of a half of the power consumption that's in that chip is coming from the I/O. It's not even the processing. It's just getting the signals on and off the chip, doing the PAM4 DSP. So if you could find a way to do this optically with lower power, it would be a major benefit to improving the chip itself.
So the real drive behind silicon photonics is lower power consumption on the ASIC, and that ultimately leads to higher density, higher throughput ASICs, because now there's more space left in the silicon in the chip to allocate it to switching bits.
So the way we've done optics forever, if you go all the way back through history, the way we sent stuff down a fiber is we turned a laser on and off really, really fast. And that worked for a while until we got to about 10 gigabits per second, and we thought that was the fastest we'd ever have to go. We'd never have to worry about it again. The problem was we couldn't figure out a really good way to go beyond that. And you've mentioned numbers here today, like 50 gig and 100 gig and 200 gig and 600 gig. Those were not possible the way we used to do things. So we had to come up with a new way of doing it. And what people did is they looked at what was happening with satellites. And they said, they've done some really cool stuff there where they use different levels and they were about phase modulation and all this really cool stuff to go over what is essentially a lossy medium. We don't have a really good way to do that with optics. And a couple of people came up with some ways to sort of do that with indium phosphide, but it was really expensive and really hard to do. What silicon photonics did is it took all of that complexity and said, let's move it into silicon, which we already know how to do a whole lot of stuff on really cheap. And it has allowed us to do those things. So yes, silicon photonics is going to be great for putting stuff onto chip, but that's way in the future. And it's not even clear that that's ever really going to make sense in most cases. Largely what it has done is it has allowed us to create these transponders that have interfaces that can go above 100 gig and can do it relatively inexpensively. That's where it's really, really coming to its maturity and change the industry.
So I see silicon photonics talked about a lot in terms of 25, 50 gig and 100 gig Ethernet interfaces for LANs.
Yes.
And they're using silicon photonics in those to replace what we used to use as lasers. Is that correct?
Well, it's still a laser.
Yep.
It's just the way they're modulating it. Used to be, Andrew mentioned lithium niobate. That's a device essentially that can turn a laser on and off really fast. It's a modulator. Silicon photonics doesn't just turn it on and off. It puts something in front of it that moves it at multiple levels and multiple phases and allows us to do things like PAM4.
Okay, so now you're starting to transmit 6 signals on a single frequency.
Well, you're starting to transmit symbols rather than bits. You're transmitting a symbol. And that symbol means one of, say, 16 points or one of 64 things. So you're getting a lot more information out of it without having to turn it on and off quite as fast.
Okay, I'll put a link in the show notes to pulse amplitude modulation for Wikipedia. You'll get some sense about what that is, and also quadrature amplitude modulation. I think if you've been listening along to the podcast, you might remember we've talked about those in terms of Wi-Fi, which is where they're used mostly. It's the same principle, though, isn't it?
It's exactly the same.
Yeah, the one thing I'd want to point out, though, is you go look at some of the transponders today that are used in the data center that are built out of silicon photonics. You can buy something that's functionally equivalent that has no silicon photonics in it at all. And there's not a really big difference in terms of cost or power between the two solutions. And the big company that's pushing silicon photonics is Intel. And you can go look at their LR4 or their CWDM solution for 100G. And the benefits over the traditional way of doing things aren't really that clear yet. So I think the one thing I'd want to point out is that while there are people doing silicon photonics, it hasn't become like a no-brainer, like, oh my gosh, why would we ever do it any other way? We haven't reached that stage yet.
At least for short reach. Yeah. For longer reach, it's a different story, right?
So for short reach, its cost is a driving factor because people are only, if you're going to drive 50 meters or 100 meters of Ethernet on a fiber optic cable, you're not willing to pay $50,000 per interface.
Yeah, but you could buy something from Finisar or you can buy something from Intel, and they're functionally equivalent. They can even interoperate with each other, but there's not a major difference in terms of the cost of the power of the two solutions. And that's why there's still a tremendous amount of old school stuff being sold today.
So just to wrap up the cut, because I heard a lot about silicon photonics and I do try and check it. So really what you're saying is for silicon photonics, where we're probably going to use it is on chip. So we're actually going to use optical interconnects inside the chip, but less likely to be outside the ASIC in the future.
I wouldn't agree with that. I think there are certainly people out there who believe that we're going to be able to put it onto the chip. I worked with a startup company out of South Africa for a while that was trying to do this, trying to actually get light out of the silicon and do some interesting things. There are reasons why. I think about a Broadcom chip right now and how would the interfaces look on it, and can you imagine putting into that lasers that have to attach to it for all of the interfaces? That might work in some cases, and I know there are people out there that are pushing that, but there are going to be a lot of cases where you're going to want the Broadcoms of the world to focus on what they do best, and then let somebody else worry about the innovations in optical, and still have that that serial interface or whatever that interface happens to be to some sort of optical external to the device to allow you to go over distance.
So there's some hope that this will give us something over time, but there's obviously some sort of innovations or some sort of step change in terms of the material science before that works, because putting a laser onto a silicon substrate in a 10 nanometer process isn't going to be
There's
easy to
still a
do.
lot. There's still a lot of work to be done on the manufacturing side because, as I said, there's people building the same transponder with two different technologies. One using silicon photonics, one that isn't, and they're both competitive in the marketplace. So the silicon photonics hasn't proven itself as the no-brainer approach to doing these things as of yet.
Okay, so something to watch, but not something that people in the field would necessarily need to worry about because it's something that happens inside the box or inside the transponder.
Right.
That's correct.
That's correct. Yeah, you talked a little bit about data center interconnect and the idea of going between data centers when you're talking about longer distances, not inside but outside. In that area, I think silicon photonics is generally considered an enabling technology. It's what allows us to now have 600 gigabits per second per wavelength and then 88 wavelengths. So multiple terabits per second on a fiber. That's really the enabling technology. There are some competing ones, but not many.
Right. And so there is some so this means that whereas in, say, data center networking, everything's modular, everything's componentized, everything's interoperable to a lesser or greater extent. Some of it's imaginary from the vendors and some of it's real. There are wide range of differences between the transponders and the approaches that vendors take. So you wouldn't necessarily have different vendor equipment talking to each other. You wouldn't just be able to plug in two vendors' boxes and expect them to work like we do with Ethernet.
That's an interesting question that we could spend a lot of time on. There are groups within the industry that are trying to make it work. And generally what happens is you can make them work as long as you make them work at the lowest common denominator over the shortest possible distance with the fewest bells and whistles. Those will generally work with each other. But if you want to start going over longer distances, vendors have different special sauce that they've thrown in there that make them work. If you want to have programmability, you want to have them be able to do interesting things with switching and auto balancing, then you start not having compatibility across vendors. And there are groups like Open Rotom and some other groups within the industry that are trying to standardize that so that you can say it'll work. Over short distance, usually not a problem. Over long distance, you can't guarantee it all the time.
So where you were talking about 600 gigabaud over, I'm trying to remember the numbers off the top of my head, that would probably be proprietary. Like you're right at the leading edge of where you are, but you could probably have an interoperable standard if you clocked it back to something like 200 gig and a 16 QAM on a single carrier.
You might not clock the speed back, but what you do is clock back the reach performance. And that's the thing with standards is once you start requiring interoperability between two vendors, as Scott said, it's the least common denominator. And in the past, there's been such a huge focus on performance that people have been willing to forego standards to get the most performance out of the optics.
I see what you're saying. So much of it is about if I drive the signal at this level on this fiber optic, because a big part of optical is actually the fiber optic itself and its ability to propagate a signal at a given power level.
Yeah, it's not so much the power level. Generally, it's something like forward error correction, and that may be something you're not familiar with, but if you are, it's something that's been done in radio and other signaling for ages. Essentially, you look at what you came in and you're able to figure out if there were errors and correct them. The ways that forward error correction is done, there are standard ways which are pretty good, and there are proprietary ways which are really, really good. If you use a proprietary forward error correction, you may get an extra 100 kilometers or so out of your, well, maybe 20 kilometers out of your distance. So the power levels don't really change, but the coding changes.
Right. And for a given fiber optic situation, so if you're buying dark fiber from a given provider, they might run, one path might run 150 kilometers, but your second fiber optic path might run 300 kilometers because you want a redundant path.
Exactly right. Or it may be a worse fiber. It may have more connectors in the way, or it may have old fiber. It's not necessarily distance, but it's how good the fiber is. But that's exactly right. Yes, some of them will work better than others.
I always forget about that. When you're talking about fiber, it's not actually how far it is. It's basically how much power gets taken out of it. And that power sum is really the key. And that's the, how many connectors there are, because every time you cross a patch lead, you lose X amount of power. Different type of fiber optic cables attenuates the signal at a lesser or greater degree.
Right. And if it's aerial and it gets caught in the wind, it might lose something. If it's underground and goes around a corner, it might lose something. Yeah, fiber optics is really interesting.
Yes. All right. Well, I think we've probably covered, I think we could probably actually do an entire show on this, and I'm kind of fascinated about it. Just to wrap this up, if I was a network engineer and I wanted to understand what it is about transmitting fiber optic signals? Give me three key factors. Let's go with one from each of you. What are the key things that you think somebody should be looking at if they're looking at propagating a DWDM signal in terms of optics? Andrew.
I would say, if you're not going to be using an optical solution from a vendor and you're going to try to do it on your own, I don't know.
So you'd say
it's complicated. There's no one thing.
I guess what I just want to look at the ROTM and the transponder and say, should you go with one vendor's set of transponders or one brand of equipment because that's really the only way it's going to work today?
Unless you want to spend a lot of time understanding how all this stuff works, absolutely.
Right. Scott, anything to add?
Absolutely, and it's not just the hardware, it's not just the optics, it's the software that controls it. If you're buying from a lot of different people, you've got to have lots of software controlling all of the different parts, and sometimes those pieces don't work together. So it'll be fine when you put it in, but then when something breaks, it'll be impossible to figure out what happened.
All right, so since you've started talking about software and the control plane and the devices, let's move the conversation along to what I broadly talked about, optical devices. Now, in the preparation discussion, we talked about there's actually two types of optical devices. There's optical switches, which are the ones that actually just switch the optical signal or the wave, the optical wave as it comes in and then propagates it again. And then there's optical edge devices, which do Ethernet to optical or physical to optical. How big is that market in enterprise networking? If you're a network engineer working in enterprise IT, I think there's questions for Andrew. How big is the optical networking market in enterprise networking today?
Well, there's $14 billion worth of optical hardware sold every year, and about 10% of that is sold directly to medium-sized enterprises and large enterprises. Most of the equipment gets sold to the telcos, everyone from Verizon, Level 3, and Colt, and China Mobile, China Telecom. So enterprises are a small portion of the purchases that are out there, and there are a few vendors who tend to cater more to those types of clients.
Is the enterprise networking more profitable than telcos?
I would say it probably is more profitable, and particularly on the service side. And there's a lot of system integrators and things that will work with, let's say, for instance, a Ciena or a Cisco or an ECI. There'll be a system integrator that will take that equipment and then work with the medium-sized business like a hospital or university to actually install it and turn it up.
So, Scott, you're doing this with enterprises today?
Yes, we are.
What are the sort of challenges that enterprises are facing when you turn up on their doorstep and start saying you should do optical here?
So I like to tell the story. We went into a large financial institution one time that had been paying a lot of money to their I guess, what did you call it? The least horrible?
The least worst.
The least.
I would never call a telco the best.
Yes, they were paying a lot of money to the least worst to connect a data center together. They were building a new data center, and so they came in, brought us in through a partner. Like Andrew said, a lot of stuff is done through partners, and said, tell us what it would be like to build our own optical infrastructure. And we came in as the optical experts and started talking about wavelengths and dB and splicing and performance, polarization, modulation, dispersion, and how easy this was. And we terrified the hell out of these guys. They had no idea what we were talking about.
You were talking in a completely different language, I imagine.
It was. And not only did they lose that sale, they didn't sell the optical. They almost went to the telco and just gave them their data center business because they didn't have to deal with that. So we learned a great lesson there that the biggest challenge for these guys is talking in a language they understand and convincing them that this really isn't that hard. Everything we've been talking about, things like silicon photonics and chips and putting things on chips and off chips and building transponders and ROTMs, they don't want to hear that. They want to hear this is a way to connect things together very easily.
Yes.
So the next time we went in, we said, look, this stuff is just virtual fiber. Lease a fiber, we'll give you virtual fiber on top of it. You go from having one connection to having 80 connections. It's easy. That is honestly the biggest challenge in optical networking that we've had run into with enterprises. Yeah.
So this is something that I've often talked to people about is just go and get some DWDM gear, plug it in, and you'll get two dark fiber paths or redundant fiber paths through your building, plug it into two different boxes. And every time you plug the boxes together, you'll get 24, 48, 80. Out of that one fiber optic run, you can have 24 to 80, 96, 10 gig, 25 gig, 40 gig, 100 gig lines out of it. It's magic.
Exactly.
It's like this infinite bandwidth loop,
If only it was infinite. Yeah, unfortunately,
Yeah.
there is a limit, but yeah, it's amazing, and it's been, I guess, since it was introduced back in the 90s, it has absolutely revolutionized the way optical networking works.
Mm. So literally, it's a case of put a box in, connect it to the dark fiber. There's some monitoring that has to happen. This has some setup that has to happen. But at that point, you've really got a box at the edge which has X number of Ethernet ports, usually 24 10 gigs or 24 50 gigs, I think is fairly common these days. And then the other side is this optical thing. And then you can just mux all of those interfaces straight over that one fiber pair.
Right. There are lots of different ways of doing it. People have put it together in different form factors. Some of them you put everything in on day one. Some of them you build over time. Some of them running at 100 gig. We have 200 gig and 400 gig. And by the end of the year, we'll have 600 gig. Some people only want to run at 10 gig. So there's lots of different ways to put it together. But essentially, that's exactly right. You plug it in, it hits these optical things, and it goes over the fiber. And it's very, very simple.
How many customers that you've worked with have actually know much about the optical? Can you just buy this stuff and plug it in and use it? Or do you need like magic robes and wands and special arcane incantations to make it work?
What we tell people is you don't have to have any optical PhDs on staff. We have those on our staff, and we'll take care of that for you. So we had a customer recently. It was actually a utility that was trying to build their own because they had this issue where when their communications network went down during a power outage, they called up the local provider and said, "You've got to get the communications back up so we can turn the power back on." They said, "That's great, but as soon as our power gets on, we'll do that for you." And so they decided to build their own, but the problem is they knew nothing about optical. And so they were actually acting sort of as the enterprise connectivity for a bunch of power generation and distribution companies. And they were terrified about this. And we came in and showed them that really, once you've got the connectivity and you've got the software on top, then software has gotten very intuitive these days. The software on top will tell you things like, this laser is about to die. Go buy a new one and put it in there before it breaks. Or someone.
Hang on, can I just want to do lasers die?
Yes, they do.
Sure.
So they just wear out?
Everything breaks.
But you predictively so? Like it's not just like was working, now it's not? And you can actually predict that the laser is like, is it physically like an organic style thing where it degrades over time and needs to be replaced? Or is it?
So I actually did my graduate research on that. So depending on how deep you want to go into it, essentially what happens is lasers these days are built out of layers of semiconductors and electrons flowing through those. And over time, those electrons start burning little holes. And if you get more and more of those holes, it stops working as well, and it takes more current to do it. So what you can do is you can watch the current on the laser, and as that current starts to go up or down, it tells you that the laser is getting bad. And so before it even breaks, you can know that the laser is starting to go bad, and you can go out and fix it.
Andrew?
Yeah, and on the receive side, the software can detect the amount of light that's being received, and over time, as that starts to degrade, you can say, well, we're getting close to the end of life. There's a problem, or you can even sometimes it's not even the lasers; it can be the fiber. Over time, the fiber will degrade, and that you can detect that just by monitoring the link, and that's where the software that Scott's talking about is so important.
Now, it strikes me that this would happen to Ethernet fiber optic things as well, but the power difference there and the timing differences, because they're running relatively slowly compared to these DWDM, you're talking 600 gig, and yet we're running them at 25 gig. Even though there's some variation and degradation in enterprise, it strikes me that the degradation would have much less impact than you would on an optical rig. Is that a good statement?
Unfortunately, no. It really doesn't matter all that much because the lasers really aren't running at all that different power in general. They have an amplifier outside of it that's running the extra power most of the time. And the slower stuff generally will last a little bit longer, but you still gonna have the same issues. Usually, the issue with a switch is that when it starts to die, you've got a redundant piece of it that's there, and you can swap them out relatively quickly. When you're talking about a link that's going thousands of kilometers, or even hundreds of kilometers, you want to know about it long before it happens because that impacts a lot more things.
It tends to be a critical thing. There's usually dozens of services layered over the top instead of just one server.
Right. Now, we also have software built in. This is one that's kind of cool, that if somebody cuts the biggest problem with a fiber optic link is not usually the laser dying. It's usually somebody with a backhoe going through it.
Oh, yeah.
And so we actually have software as well for these guys who really don't know anything about optics. Remember that. They can tell exactly what location that fiber break hit. So they can send a crew out to specifically that location to do the repairs. So they don't have to be able to know a lot about optics and figure out where everything is. So all that software on top is really what makes this almost a no-brainer.
So you send a signal down, you get an echo back. You can say, "Oh, I've got 151.2 kilometers down the wire." And they can then look at their maps and work out where to dig a hole.
Yeah.
Yep.
And in fact, you can use those tools to even, if you're a lot of the equipment has such sophisticated features like that in it now, where you hook it up to a fiber, you can actually go and find the poor performing splices and things like that. So
Absolutely.
when someone tries to sell you some fiber, you can say, well, that's great, but before I actually buy this thing, you need to fix this splice at 120 kilometers because I'm getting a lot of reflections on that.
That's beginning to sound like magic.
It's really cool stuff.
That really is. Now, that used to be really arcane, like using these devices. I did some work on this stuff 10 years ago. And I mean, painful does not begin to describe how these devices worked. It was like, the devil was going through my head and poking me with his trident every single time I wanted to do something. It was not intuitive. It was not obvious. Everything was arcane and stupidly put together because vendors obviously hated their customers. Have things changed?
Well, yeah, you don't have to wear the robes anymore.
But you still must you have to respect the physical layer. That's the thing. It seems really simple from the outside, but when you get into the details, there's a lot of things that can go wrong.
But for example, to make it simple, our software package, you don't ever actually have to go to the device. If you know that something is broken, we have a point and click that you click on that says, "I know it's broken. Tell me where it's broken," and it comes up and tells you with a map. Here's a map of your fiber layout, and here's a little red dot telling you where it's broken. So if you want to put the robes on and know all the stuff underneath it, we'll certainly give that to you. But the software now has abstracted all of that away.
So what we're seeing too in the optical market is, in the old days, it was all optical Ethernet. But increasingly, we're starting to see optical devices which are IP MPLS optical. So recently, for example, Juniper bought BTI so that they've now got this optical capability that they can now do IP and MPLS and optical in a single box. Is that something the optical vendors are getting into, or is that something the networking vendors are getting into, or is it's a free-for-all and everybody's converging on that IP MPLS edge?
This has been going on for over a decade, really.
Amen.
Almost 2 decades. This is nothing new. Cisco was really the one that first started pushing this 15 years ago. They called it IP over DWDM. And what they would do is take the high performance optics and then strap it right on the front of their routers. And that's been a good tool for collapsing the transport functions and the layer 2 and 3 functions into a single system. But when you do that, there are some downsides. Typically, the biggest one is in terms of density. If you look at 100 gig coherent interface on a Juniper system, you're going to get half the density of what you would be using just if you had the shorter reach client optics. But you end up paying the same amount for that slot. So that's one of the big challenges.
Yeah, we get asked about this a lot because there are people out there who are pushing this idea that the optics need to integrate directly into it. But even what Juniper did when they bought BTI, they still have those as separate devices, and they're still talking about the Juniper box being a separate device. Andrew hit on one of the big ones, which is density. There are several other ones, but for example, there was a talk at OFC, which is a big optical conference, a couple of years ago, and we had one vendor up there talking very much about their idea of collapsing it together. And then you had somebody from Google saying they were doing exactly the opposite, that they thought their optical expertise needed to stay at the optical layer, the optical capabilities need to stay at the optical layer, and that allowed them to focus on the switching and routing as a separate entity without having to burden it with the optical capabilities. So you think about the things we were just talking about, things like being able to figure out where a break is in the fiber, being able to determine whether lasers are failing, all those kind of things. Most of that will never be integrated into a switch or a router. The real estate is way too expensive.
I'm gonna make a note of that and call you up when never happens. I do agree.
The future is here. It's just not evenly distributed, right?
Yeah,
so people are using that, but in most cases, it's not going to work because you're not going to get the tools that you need to be able to debug and manage your network. But if you look at someone like Microsoft, like the way they're hooking up their data centers in all of the big cities in the United States, if it's 40 or 50 kilometers, indeed, they've completely eliminated the need for external optical transport equipment. They're using pluggable optics. Yeah. But once they need to start going longer distances, then they move to the more traditional model. So there's cases where it does make sense to take this approach.
Yeah.
But I mean, these are people who have, essentially infinite layer 2 network management experience, yet they're still externalizing and pushing the optical transport gear into its own discrete function.
Okay, so what you're saying is for today, it makes sense to have optical devices with optical software, optical control planes that are optimized for that purpose. And while we might drop an optical interface into a router to simplify short haul, but for long haul, it still makes sense to have them separated.
In a lot of cases, yeah. I ended up writing a white paper on this because I got asked the question so many times, and the conclusion was that there are cases like Andrew mentioned, like what Microsoft is doing, where it will make sense. But if you're talking about doing a data center interconnect with multiple WDM connections, a lot of times you're going to want to keep those separate. In fact, most times I would say you want to keep those separate.
Well, partly that's a failure. It's also an operational issue when to my mind, there's sufficient divergence in optical operations from IP operations that mixing those skill sets together, there's no coherence. It doesn't make sense.
That's absolutely true.
But that over time, what we've also seen is that 10 years ago, 15 years ago, when MPLS hit the market, people who did MPLS didn't know how to spell IP. They only did MPLS. And yet over the last 15 years, we've seen that market converge where MPLS is now a commodity skill. When you go and do your basic training, you get to start learning MPLS from day one. It's not a mystic incantation that you learn as an advanced magician.
Right. And I think this is one of the, I would say a mistake that a lot of people make. I know we're going to talk about at some point, things like white boxes. When you look at Ethernet versus IP MPLS versus white box switching and routing, everybody says, well, look how all of these things have gone from being separate things to being together. And I would agree with that because they're all packet-based devices that can be done on a chip. They all have a similar underpinning to them. And as Andrew mentioned earlier, when you start talking about optical, you've got to respect the physical layer that those guys don't have to worry about. And so you're talking about a completely different type of technology. It's like saying that you're going to integrate the radio frequency transmitters on microwave towers into the devices that switch cell phone calls. They're just such completely different technologies. I agree they're always next to each other, but you're never going to have somebody who understands both of those at that level.
And the cadence of these technologies, like they're not necessarily developed in sync, where Broadcom is releasing new Ethernet switches, but optical technology could be on completely different time cycles. So you don't want to necessarily couple these two things together, because once they're coupled, you're going to lose the flexibility to pick and choose the technologies as they come to market.
Okay, so if the market was to slow down and converge and realize, if there wasn't an enormous demand for bandwidth like we see now, and therefore financial rewards for the companies that make these optical interfaces, these high-speed transponders, we could see a convergence, I guess, but the chances of bandwidth reducing is pretty small, to be fair.
Well, on a side note, I'll just point out that most of these people making these optical transponders, this isn't known to be a very profitable or highly lucrative business. It's pretty brutal. So if we got to a situation where they were making tons of money, I think they'd be happy to deal with whatever problems come up.
I want to jump back to one topic. One of the things that we missed when we were talking about optical components was you made the point about lasers actually wearing out, because over time the electrons that stimulate the laser start to drill holes. Does that mean that there is a quantitative difference between quality of those optical modules? One of the things that we see is vendors like to charge, or anywhere from 5 to 50 times what it costs to buy a standard SFP module, say in the Ethernet space that I know well. And you can go to an online store and pick up a module for $50, but a vendor wants to charge you $1,500 for the same module. Is there a qualitative difference there? Is the laser better made, or got some sort of special magic inside?
Yes.
I have a funny story. So there was a very large OEM, let's say, that makes optical modules, and they received a shipment from a equipment manufacturer that said, we're having massive failures. All these modules that you guys have sent us are pure garbage. Take a look at these, do an analysis, figure out what went wrong. And so this optical component vendor, dutifully took all of these components from the big, large customer, took them apart and figured out that they were all counterfeit, clones, copies. They didn't even make them. So absolutely. There is a huge difference in quality among all of these component vendors because so much of the cost and so much of the process isn't just getting the laser chip. If you ever look at a picture of optical manufacturing, you'll see, huge amounts of, touch. Like there's a huge amount of contact to integrate all of these things together in the little box. It's not like making semiconductors. There's a lot of hands-on involvement and checking and alignment. And that's not necessarily a good thing, but that's the only way that we can do it today. And if you don't do that with the highest degree of quality and standards, you're going to get failures.
Okay. So does that matter less at the enterprise level? So I've seen plenty of people buying the cheapest possible optics and saying they're having perfectly acceptable results. They don't get many failures, and so much money's being saved that it doesn't make sense to buy the more expensive ones. Does that make sense in terms of an enterprise, or is it different? And, we talked earlier about how, when you're doing optical networking, you've got hundreds of services running over a single thing. So it makes sense to stay with the higher quality stuff. Is that fair statements?
I think it depends on the customer and their tolerance for problems. Like, I mean, if you don't want to have any problems, then you're going to go buy the good stuff. If you're willing to have a failure rate, you can take the chances. There's another thing that's going on here, though, that has nothing to do with failure or manufacturing quality, and that is large companies like Cisco or Juniper. They will, in essence, require that you buy modules from them. And they will, say, look, if you don't buy modules from us, then we're not going to warranty the product. And they will then sell you the blades at cost or below cost, and then you have to buy the modules for them. And in a way, they're providing a service where you can start to pay as you grow. So if you only need one or two ports on day zero, you don't have to buy all 24. You can buy them one by one and plug them in.
Yeah,
but what the large hyperscale guys have figured out is that this model doesn't work for them at all, because right at the beginning they need to buy everything. So this variable cost model is no value.
I call that the sucker sell. Oh, there's effectively a licensing fee when you have SFP based switches. Every time you buy another SFP module, you're paying a license fee to use that port.
That's right. But if you're only buying one port, it might actually work out to your benefit. If you're buying a lot of ports, then you're right. You're a sucker.
Yeah.
I'm just glad that Andrew answered that question instead of me, because we do exactly that. We do license per port, and it is true. And I actually have had this discussion before with customers who are intelligent enough to understand this and sophisticated enough. They understand that they're getting a deal on the hardware. They're buying the razors really, really cheap.
Yeah.
And with the stipulation that they're going to buy razor blades.
They're buying the handle really, really cheap.
Right, and they're going to buy the razor blades from us going forward. Because if we had to make money on every card that we sent out there, and you're going to buy the optics from somebody else, the cost of that equipment would have to go up.
Right. So you're saying, so I guess to summarize my equipment, there is a difference between the modules. You need to be willing to have some sort of tolerance. You might get a batch of faulty ones. You might get a batch of good ones. It can be hard to tell.
Yeah, and there's also an in-between. There's companies out there now who will purchase gray market modules, test them, make sure the quality's good, and then allow you to use them in your Cisco or Juniper or Ciena or Cisco equipment. So there's the mid-market guys. But if you go onto eBay and you buy something, I mean, you have no idea what you're going to get.
Now there's also software in those modules as well. Is there features in vendor-approved modules that don't exist in the lower cost options, in the generics?
Sometimes, yes, yeah.
Right. It's not always the software. Sometimes it's the what's built into the inventory part of the module, so that we have the ability to figure out it. And so, for example, we can go in and tell who manufactured it, where it came from, what the lifetime of it is expected to be, and then sometimes we have access to certain counters in there, bit rate failures and those kind of things that you might not get out of some gray market module.
So the sort of features we were talking about earlier, like finding where a break is in the fiber and being able to do reflecting. Calculate the reflections coming back from the break. Would you be able to do that with a generic, or would you need a vendor-approved optic to do that?
Yeah, that actually switches over to a different optic because it runs at a different wavelength, so it doesn't interfere with traffic.
Right.
So that one you would, but the ability that Andrew mentioned earlier about, for example, being able to look at the laser changing current over time, or being able to see what the receive power is and see whether or not it's going up or down, you may not get those capabilities.
Yeah, they wouldn't be in the software. That's something the vendor might develop separately from the module manufacturer.
It could be, sometimes. And briefly, Andrew also mentioned the idea about warranty. Now, we do have experience occasionally with some of these third-party devices going into our equipment and generating a lot more heat than they're supposed to, and it does damage the equipment, which is why warranties are not valid when you use third-party as well.
That just sounds like self-serving rubbish.
It does, doesn't it? But I've actually
seen it really does.
Because you get some of the stuff that comes out of these really gray market or even black market stuff, like Andrew was working about, where it doesn't really work. And we've had some of them that put in that just really get hot, incredibly hot. And the heat handling on these devices is crucial. It's very, very hard to get all the heat off of these. Data centers are designed specifically to have airflow from a hot aisle to a cold aisle, because cooling these things is almost impossible. And so when you put a device in,
we're talking about RODMs here. We're talking about optical.
No, I'm talking about the optics that you plug into a router or you plug into one of our devices.
Right.
Those little devices are the cards that hold them have huge heat dissipation capabilities built into them. And if you put something in there that uses a lot more heat than it's supposed to, it's going to shut down.
Or worse, it could actually create enough heat to actually thermally damage the board that it's on or the connector.
It could, yeah. Now, if you've built it right, it'll shut down first. But yes, it could damage the equipment.
Okay.
I think the rule of thumb is if you're going to buy something illegal, make sure you have a good dealer.
I just want to probe this a little bit more, because this is a real pain point for a lot of people. Is this something that happens a lot, or is this just something that's one of those apocryphal stories of, I put my switch in the rack, I plug it in and it blew up and then the rack caught on fire and wow, that was a great day.
I think the dirty little secret is the people who buy a lot of this stuff.
Yeah,
they've negotiated the price of these things down. Right. This is a negotiating point. So when you get out toward the edges of 5% of all the volume, and people are trying to save some money because they're running medium-sized businesses, then it comes up from time to time. But if you, like I said, you go to eBay, you have no idea what you're going to get. But if you spend a little bit more from a reputable dealer, somebody who's actually
there are companies online who've been doing this for 10 years who they were dumping really
put their
bad
reputation on it. So then in that case, you're probably going to be all right, particularly if you're buying shorter reach, optics that are highly standardized, where there's really not any way to differ. They're commodities. It's just like DRAM.
Yeah, which is a great segue, talking about commoditization. Now, over the last 10 years, I've seen a number of efforts around open optical. This is sort of like an attempt to drive into like a white box Ethernet, the idea that there are standardized components that can be put together in similar ways, and that you can buy an operating system that goes on top of it and it'll look just like an x86 running Linux, and it will work just like an x86 running. Why do we have to have these proprietary boxes? I guess I'll start with you, Scott. Do you think open optical is going to be a market transition? Are we actually going to see more open optical enter the market, say, soon or over time?
Yeah, this is something I spend a lot of time with educating internally and externally on. Facebook in particular, when they came out with their Voyager project, this idea that you would have a completely open optical system that has some transponders built into it from a specific vendor, and it has a Broadcom chip built into it, then therefore this would make everything much less expensive. Really hasn't taken off. There's a lot of reasons for that. One is the stuff we talked about earlier. There's a lot of capabilities built in, like being able to find a break and all those kind of things that vendors have done. The other reason is that it's not clear that there's any real cost savings, because we're all essentially building the hardware almost the same way. We're coming up with different ways to put it together, but there's not a huge difference. We're all buying chipsets that do optical. We're buying chipsets that do switching. The reason that ours work better is because of the software we put around it, the expertise we put around it, the building it into form factors that make sense in different locations, and the fact that we can innovate a lot faster than something like that. If a new chipset comes out that's faster, for example, the Voyager project has not taken that on board yet, we're able to immediately integrate that and come up with something new. So it was an interesting idea. I think I brought this up earlier. This idea, people look at white boxes in switching and say, well, that has been such a great success. The Facebook white box switch has done amazing things for Facebook. Why can't we do that with optical? And as Andrew said earlier, you've got to respect the physical layer. It's not like you can virtualize a laser. We've still got to make a laser work. We've still got to get it to go across a specific distance at a specific rate. It's not like you can take an x86 and make it act like a laser. So I don't know that this is going to be a huge industry changer. We hear about it a lot from universities, in particular. They all like the idea. They think it's going to be really cool, but we haven't seen anybody except adopt it on a widespread basis. We haven't seen it take off very well. We still think that the individual vendors have ways of proving that they are what they're doing has value. Now, there are other groups within there, like I mentioned.
I'm going to be a little inspirationally cynical there and say that people said the same thing about white box Ethernet 5 years ago. And then and look at what we've got today, where fundamentally that model is now becoming slowly but steadily the standardized model. Cisco's disaggregating its software from the hardware. They'll run on white box. A lot of people are starting to run white box Ethernet as their primary. They still run the proprietary stuff in certain places, but a lot of the white box. I mean, the most extreme, of course, is that Amazon now is moving to all white box, all self-developed white box.
Yep. But what was the reason? Why? What was the engineering problem that was being solved? Because I think that's the thing that you have to ask with optics is, with the white box in the switching area, one of the big things that was attacked was the cost. Right? These companies are making 70%.
The cost was important. The capital cost was important. But the thing that really bothered the bigger companies like Amazon, Google, and Facebook, and I've spoken to people in those organizations, was that vendors can't develop software at a level of quality that is acceptable to them. And when bugs are found, as they are always, they're not able to fix them in a timely fashion. Vendors want to take 6 months to 2 years to patch a bug. And these companies say, I need it by tomorrow. And they're just not able to do that. That was the real money that they wanted to save.
One of the things that we've seen in the optical area is that the market has the people who make this equipment have responded and built these new, I call them compact modular systems, and they look like white boxes, except you get the benefits of the equipment vendor's supply chain and sourcing all these things. But from a software perspective, they're very open. I mean, you can go to a company like Cisco and you can buy one of these systems, and they'll ship it to you, with is bare metal.
Yeah, and like an NCS 1000 type thing.
That's exactly right. And they're not the only ones doing this. Ciena's doing this. I imagine ECI is doing this. They're basically like, look, if you don't want our software, that's fine. If you have the expertise to design this and make it all work, go right ahead. But in the case of most companies, including a lot of large legacy telcos, that's just not the case. So you can buy these systems, essentially lobotomized and put them in place if that's what you want.
And if you've got that sort of skill. But again, it comes back to, like, I can see the other side of this equation. If you're running a data center interconnect and you're betting your entire business on there being, 150 gigabits of bandwidth between those two sites, you can't afford for that to fail. If you don't have the in-house expertise, or if you've got hundreds of services running over the top of that, you need that to be absolutely the best that it can be, and you can afford to blow vast sums of money buying overpriced vendor-branded equipment and not go down the white box path to cut corners.
And look at the magnitude of the problem. You're talking. I mean, of course, Amazon is moving to all white box switches, but what's the magnitude that they spend on those versus what they spend on the optical layer? Right. It's
Amazon is now spending more money on data centers than Cisco makes in a year. They're spending $20 billion in capex a year. Cisco will take about $12 billion in revenue this year.
Right. One of the differences that Amazon sees those optical interconnects as enabling them to make money, whereas a telco sees those optical interconnects as the way they make money. It's a very different way of looking at it. We talked to one of the interesting stories. We talked to a financial institution one time, to your point about whether or not they're willing to spend more money. And we were talking about saving some money on an optical interconnect. And the guy stopped us and said, I want you to understand, we don't save money with optical interconnects. We make money with optical interconnects. Yeah. We'll pay whatever it costs to make sure it's up and running. Not to say that these are more expensive. I think one of Andrew's points was that building it by one of us, as opposed to going out to some white open project, doesn't necessarily save you money. Where you make the value is on the stuff that we put on top of it.
Which, value adding, I'm always a little cynical when people say we've got to value add. Over the years, that's turned into something a little bit distasteful, and this is why white box is working for networking people.
And that's true. I was with a large university in North America recently, and I gave that same argument and got the exact same argument back. Well, yeah, but we can figure out how to make this stuff work. And to Andrew's point, well, if that's true, then that's fine. We'll sell you just the equipment with no software. But buying that from us as opposed to buying it from somebody who's putting it together based on a blueprint that was put together by Facebook doesn't necessarily have any value.
The Facebook Voyager project was interesting because I talked to people who evaluated that system, including some carriers, and they got it into their labs. And I talked with them afterwards, and they weren't planning on using it, but they said that it taught them something very valuable. Is it taught them how dependent they were on their vendors to basically close the loop in their network and make things work. Is a lot traditional carriers. I'm not even talking about small banks or things like that. I'm talking about big carriers still rely very heavily on the engineering expertise of their suppliers to make this stuff work.
And I guess I'm still, what we did see arrive is companies like Cumulus Networks who are producing, a Linux operating system with networking apps that runs on white box hardware that does all the things that you're talking about, provided the hardware is available.
Yeah.
So there are new ways to market. And
Cumulus has a software stack for the Voyager, and
yes,
I spoke with them recently, and they're trying to figure out who's going to buy it.
Yeah, that's okay. I remember talking to Cumulus when they're trying to work out who's going to buy it for Ethernet too.
But it goes back to what we were talking about earlier, that, you could probably do that at the lowest possible common denominator. If you're going 80 kilometers with a certain number of wavelengths at a certain speed, where things are plug and play, then it might work. And that's what the Amazons and the Facebooks and all are doing. They don't care about getting the best performance. They want to be able to plug it in, and when it dies, pull it out, throw it away, and put another one in.
Yeah.
Most people just are not in that situation.
Yeah, the other problem here, of course, is that your dark fiber is expensive. It's not like you can just run an extra fiber like you can in the data center. So in the data center, you can just put redundant switches in place and extra capacity. And if a handful of those switches flame out, it's no big deal. It doesn't necessarily have a deep impact. But, buying 1,000 kilometers of fiber optic cable is a pretty expensive game.
Right, and keeping it working is a lot harder than keeping all that stuff working.
So maybe there is an argument to be said for the time being that open optical will be a much harder, much longer burn, and maybe it will never come around.
Yeah, it's inspired a lot of interesting things in the optical industry, things like disaggregation, open optical, a lot of other special little terms that are coming out and becoming interesting. The idea that maybe you want to buy a box that just has transponders in it as opposed to buying one that can do transponders and amplifiers and everything else. So we're really trying to figure that out right now. The industry is fracturing somewhat between what the data center guys want and what the telcos want. And it makes it really exciting for us to have to figure out what to build next year.
It strikes me that there's like a whole bunch of standards that optical seems to have missed in a way, and there's been good reasons for it. Like you said, if you can develop a technology which can get more carriers on a given optical fiber, then more power to you. Because as I said, 1,000 kilometers of dark fiber is a very expensive business just in lawyers' fees alone.
You just rewind the clock 20 years. There was no need for standards, right? It was AT&T. That was the standard. And so
well, in America that was true. That was different in Australia.
Okay, in Germany it was Deutsche Telekom, right? So it was these companies in essence were so big and so powerful. They were the standard. Yeah. And the whole landscape has changed since then. And now what you're starting to see is that's trickling into the component and equipment supply chain. And what's really catalyzing that is the big web scale cloud and colo guys, because they're now building their own networks. They have the wands, they have the robes, they can do these things themselves. And that's really starting to fracture the way the equipment is being built. So you have big vendors like Ciena, and you have Cisco, and they're providing the real high touch, high complexity devices to people like Verizon, and then they're also stripping out and lobotomizing the equipment to give it to someone like Amazon.
Yeah, I do think the cloud. I mean, Google's now saying that it has more bandwidth internally than the internet does. I think, did I read that somewhere? Their own optical backbone has got more bandwidth than the internet outside.
It wouldn't surprise me.
Just of all stats like that, yeah. But
I know Facebook at one point showed a graphic that said I think 90% of their traffic never goes outside of a Facebook data center,
which is probably a testament to how badly the Facebook app is put together.
It could be.
That's just an awful lot of traffic not doing much, perhaps.
Well, you think about it. When you upload a picture of cats that you want to share with everybody, it's got to be downloaded to all of those data centers around the world, even if nobody ever actually looks at it.
Yeah.
So all of that stuff is going on constantly, not to mention the mining that they're doing to sell. there's just a lot of internal stuff going on.
Yeah, no, I'm just being.
But you hit on a very important thing. Is what companies like Microsoft are doing is they're using optical connectivity between their data centers to, in essence, simplify their computing architecture. So
quite often they're just leaning heavily into their infrastructure to solve problems, to cover up for bad programming or unoptimized software in their cloud platforms. Like if you're running Microsoft SQL Server, we've been relying on big CPUs and lots of memory to make it faster. And one of the things that cloud companies have been doing is just throwing more and more hardware at the problem because it's cheaper than optimizing the software. And so, and increasingly, companies like Facebook and Amazon and Google spend increasing amounts of money to optimize their software to make it run faster or leaner or more efficiently, so that they don't have to lean on the infrastructure so hard. If they could develop new protocols like gRPC or Quick or all those protocols that use less bandwidth and they're more efficient, they use less requests and burn less CPU.
But sometimes it's just cheaper to throw bandwidth at the problem.
Always better to throw bandwidth at any networking problem. I'm convinced of that.
And we absolutely agree with that because we'll sell you the bandwidth.
Well, I think we've probably taken the discussion just about as far as we can go for today. We're about reaching the maximum time that we've got available. Thanks very much to Scott and Andrew for joining us today. So, Scott, why don't you tell people where people can find you on the internet?
Sure. You can find me at ECI Telecom. That's the company I work for. It's ecitele.com. They're very clever. I also have a Twitter feed, which is Scott Wilkinson with a Q at the end because Scott Wilkinson wasn't available. LinkedIn is Scott Wilkinson as well. And I do write occasionally for the ECI blog, which is at blog.ecitele.com. If anybody happens to be at the InGon event in Nice in June, I feel sorry for you, but I'll see you there.
I do read the ECI Tele blog, and that's how I found you. So I could only recommend that blog to you. You do a good effort there. Andrew, where can people find you on the internet?
Sure. I work for a market research firm called Signal AI, CIGNAL.ai. Nothing to do with artificial intelligence. I'm also on Twitter. My Twitter handle is ASCHMITT. You can also track me down on LinkedIn.
Well, thanks very much for listening to Packet Pushers today. You can find more about our guests and their details on the blog post that accompanies this podcast on the Packet Pushers website. You can find that and many, many more fine free technical podcasts along with our community and news archive at packetpushers.net. You can follow us on Twitter, find us on LinkedIn, like us on the Facebook, and rate us on Apple Podcasts. It would be really great if you could do those things. It's very helpful for us to find more audience members who would be interested in hearing more of this, and it helps keep us to producing this content for you free and openly. And as always, remember, last but never least, too much technology would never be enough.